Okay, so what we're going to do is have a look at the kinetic energy at each collision. So for those of you on the video, we'll just spread this out amongst the class. So they've all done the kinetic energy calculations using the half mv squared. So you can try this at home and see if they've got it right, but hopefully they have. So we should have the kinetic energy for each of these objects. I'm just going to put them up in red. So the kinetic energy for this one was 3.24 joules. And this one, that was the hard one, wasn't it? Given it was zero meters per second, it makes it tricky. Okay, so the kinetic energy for this one was 1 joule. And for this one, 224. I reckon 2.24 might be better. I think, so might probably check that one. It's a half times
0.7 times 8 squared.
a half of 0.7 times 8 squared. So 8 squared is 64, half of that is 32 times 0.7. Okay, we've got some problems going on here straight away. 22.4. Okay.
That's 3/4 of the.
Yep, yeah, that sounds right. Yeah, that's not what I was hoping for. Mark may have lied to me. Okay, let's have a look at this one. What's the car beforehand?
Oh, that's very hard. 1200.
1200. And the truck beforehand?
Oh, no, not 1200 joules. That's 3700. I thought you were going to go to like that.
No, that's not the answer.
270,000.
270,000 joules. Yep, they've done the calculation. And the truck beforehand is... I'll wait for that chainsaw to stop outside. Say it again, Sam, before... Yep. And the wreckage afterwards is...
186,648.
Awesome. So 182,648 joules. Okay, and looking over here, the ping pong ball beforehand, who was doing the ping pong ball before? 37.5. And the brick beforehand? 4 joules. And the ping pong ball afterwards, that was ours, Liam, what was that? 73.5, is that right?
Yeah, 73.5.
And the brick afterwards, 0.04. Okay, so we're happy with all those figures? Okay. And I'm still a wee bit worried about this one. It's not what Mark told me it was going to come out as, but never mind. So the question is, looking at these guys, the problem here, this one's gained energy as well, hasn't it? Problem is that in some of these things we've got a gain of energy, and some of them we've got a loss of energy. So this one, for example, the total kinetic energy beforehand is a lot more than the kinetic energy afterwards. So we've lost kinetic energy. Heat, sound, probably quite a lot of sound in that situation. It made quite a lot of noise. Okay, so yeah, so we've lost a lot of energy, which is what we call an inelastic collision. Okay, so that means there's been a loss of kinetic energy. So if you've lost kinetic energy, you've got what's called an inelastic collision.
Possible that you might have no change in energy?
Yes, if you have no change in energy, it's what we call an elastic collision. So no change in kinetic energy is an elastic collision, which is what I was expecting to happen here, but it doesn't seem to have come out that way, which worries me a little bit. So those figures are all right though, aren't they? Now you can get combinations of things that end up with no loss of energy. So what would have happened if, this has been a bit hairy, maybe Mark just gave me the wrong figures. What happens if this one ends up going 1 meter per second that way? So that means that would be 2 that way. And this one would be 1.6 that way. So 1.6 divided by 0.7 is 1.6 divided by 0.7, 2.3 meters per second. So then this energy here would be half times 0.7 times 2.3 squared. 1.8. 1.9. Still a little bit of a loss, so that's also inelastic. It's not, doesn't come out to be the same.
But it is more elastic
than this one. Yeah. So still disappointed that figures didn't work out. Never mind, this is the way things go.
That's why we have called it plasticity.
Yeah. So if you ever have a situation where the kinetic energy isn't diminished, then you've got what's called an elastic collision. So if you have no change in kinetic energy, you have an elastic collision. And that version didn't do it. So that's an inelastic collision. There's been a change in kinetic energy. Total kinetic energy beforehand is 3.24, and the total afterwards is 2.9. So the kinetic energy is reduced. So it's not an elastic collision. So for a collision to be elastic, the things have to bounce perfectly with no heat and sound, no loss of energy at all. So the kinetic energy is conserved. So it's a theoretical thing, but you can make up stories where it happens. You have to get the numbers right in the story, and it can work. No. So theoretically, you can make up a story where you say, ignoring these things, it can happen. But in the real world, there's always going to be some loss of energy.